All right, so this is 1.8 video 3. In the last video, we talked about the intermediate value theorem and the fact that it was what's called an existence theorem, meaning that it'll sometimes tell you that something exists even though it doesn't necessarily tell you how to find it. But what we want to talk about on this page here is that a function that is not continuous, does not necessarily possess the intermediate value property. And so let me kind of show you what I mean by that. If we were to take some function that maybe looks like this, okay, clearly that's not a continuous function. You can see how there's a break in the function. Let's say that A is over here. So we'll call this A, and then there's your closed interval there. And then we're going to say that B is here. So believe it or not, this is a closed interval because every single value between A and B is taken on somewhere. Okay, every value from A until the open circle is taken on, but then the closed circle right above it up until B means that every x value between A and B is taken on. So it is a closed interval. We definitely have a closed interval from A to B, but it's not continuous. So if we were to take and sketch over here our f of B, down here kind of is our f of A, I know it's below the line, so f of A and f of B are clearly not the same, so it really does possess every single possibility except for the continuity part. And the reason that that's important is because I'm going to put a k value in here that obviously is in between f of A and f of B, but never hits the function. There's no c value that's going to give me that specific k value in this case. So there are ways that the intermediate value property might not work. Now, does that mean you can't do it for all of them? Well, certainly this right here would have worked. That would have given me a value of k, or this would have worked, or some other pieces would have worked, but there are some that don't work. All right, so this is what I was talking about in video 2, that the intermediate value theorem can often be used to locate zeros, or x-intercepts, of a function that is continuous on a closed interval. Specifically, if f is continuous on the open interval from A to B, and f of A and f of B differ in sign, meaning one is positive and one is negative, then the intermediate value theorem guarantees the existence of at least one zero of f in the closed interval from A to B. Or in other words, if I have a continuous closed function, so there's no breaks in it, continuous and closed, and one of the endpoints is positive, one of the endpoints is negative, that means that because it's that way, every possible y value between the negative and the positive y value on the endpoints have to take place somewhere, which means that you have to have a zero or crossing the x-axis someplace. So if you look at something like number 3, where it says f of x is x squared minus x minus 3, does that have a root, or basically, does it have a place where f of w, and we just changed it to w now, equals 0 on the interval from 1 to 3? Well, again, let's go to the intermediate value property. Intermediate value property, this is continuous because it's polynomial. It's a closed interval, 1 to 3. Redraw that so it actually looks like a closed interval from 1 to 3. So let's check f of 1, and we'll check f of 3. So f of 1, plugging 1 in, you get 1 squared, which is 1, minus 1 is 0, minus 3 is negative 3. If I plug 3 in, 3 squared is 9, minus 3 is 6, minus 3 more is positive 3. So I definitely have two different values for my endpoints, and one is positive and one is negative. So f of 1 is less than 0, which is less than f of 3. So that means 0 has to exist somewhere. And we can say that that's the case by the intermediate value theorem. So we can say by the intermediate value theorem, there must exist at least one root on the interval from 1 to 3. And it is important that you can actually state these things, showing all their criteria, stating this stuff in words. This becomes very important. Now, it did not actually ask us to find the root, which is good because x squared minus x minus 3 does not factor easily, so we'd have to do it using the quadratic formula. I'm not going to bother with doing that right now. All right. One more page to go. Use the intermediate value theorem to show that the polynomial function which is given has a 0 on the interval from 0 to 1. Once again, now this is a cubic. Again, it's polynomial, but it's not going to be easy to factor. And this one, there is a cubic formula. It's very, very complicated, and not many people know it. But it's not going to be an easy one to do. So let's just show that a 0 exists. So once again, it is continuous. It's a closed interval on 0 to 1, so we're good there. Let's check the endpoints. So f of 0, f of 1. If we plug in 0, you get -1. You plug in 1, you get 1 plus 2, which is 3, minus 1 is 2. Those two things differ in sign. So just like we said before, f of 0 is less than 0, which is less than f of 1. So by the intermediate value theorem, and you can abbreviate that IVT, there must exist at least 1 0 on the interval from 0 to 1. It's not asking us what the 0 is or where to find it, what the C value is there. It's just asking us, does it exist? And it does, and we can say so by the intermediate value theorem. Okay, let's go to number 5. Once again, it's polynomial, closed interval, continuous on the interval -1 to 5. All right, so let's check this out. F of -1, f of 5. Plugging in -1, -1 squared is 1, minus 3 times -1 is 3, so 1 and 3 is 4. And plugging in 5, 5 squared is 25, minus 15 is 10. So we have a couple of issues here. First of all, I don't have something which changes in sign, but that's okay because we're not really looking for a 0. We're looking for this. Does f of t equal -2? Well, -2 is not in between 4 and 10. So while f of t might equal -2, we cannot use the intermediate value theorem to prove this. If all it's asking us to find is the error value of -2, well, yes, we can probably figure out that there is a value of -2 somewhere, but there won't be a value of -2 that can be proven by using the intermediate value theorem. We can still find it, though. X squared minus 3x equals -2. Add 2 to both sides. And then we can factor. That's going to be, what is that, x minus 2, x minus 1. So x is going to equal 2, or x is going to equal 1. And 2, excuse me, 2 and 1 are both on our interval. Okay, they're both in between there, so both of those are true. The problem is we just can't use the intermediate value theorem. So we did find the values, but we cannot use the IVT to guarantee this. Doesn't mean we can't find the values. We did, but we just can't use the IVT. All right, last one's much more tricky. So it's a piecewise function, and it's giving you that the function is sine of pi over x as long as x doesn't equal 0, and it's telling you that the function equals 0 when x equals 0. We want to know if the intermediate value theorem is satisfied. So here's the part that you have to figure out. We have to figure out, does the limit, because we need to figure out this continuous first of all, does the limit as x approaches 0 of f of x equal 0? That's the question. Because we know the function at x equals 0 is 0. So does the limit as x approaches 0 equal 0? So I'm going to leave this part to you to figure out. You remember, you need to figure out the limit as x approaches 0 from the negative side, what that is, and the limit as x approaches 0 from the positive side. If both of those values are 0, then we have a continuous function on a closed interval. Intermediate value theorem would apply. If those two things are not the same or they don't equal 0, then it won't apply. So I'm going to let you work on that one. All right, plenty enough. Sorry, it's a little over 11 minutes. Missed my 10-minute mark. Good luck.